Okay, so I'll carry on from where I left. I finally managed to make this work. And so going back, what should be the output state after we start? I just want to go back and say that we started from 0, 0, 0. We did all these operations, which you can see on the board or mentioned here. What do you eventually get? You get a uniform superposition of 0, 0, 0, 1, 1, 1. And how is it going to show up? It just tells you that the state vector has a normalization of 1 over square root of 2 or 0, 0, 0 and 1, 1, 1. I always get confused with the notation of Qiskit because we have to read from the right side, left side. Some softwares use it from the left, start from the right. But in this case, it doesn't matter. So that's nice. I don't need to tell you which one is 0, 0, 0. And this is what we get. Okay, so in this part, I'll talk about some quantum algorithms which people have been thinking and developing for understanding not really a quantum algorithm, but it's like a hybrid classical quantum algorithm. It's called hybrid because there are some parts you do on a classical computer or using classical setup, and some parts you do on a quantum machine. Why you cannot do a full-fledged quantum? Because probably we don't have efficient classical quantum algorithms to do, say, optimization or gradient descent and things like that, which are needed to, say, for example, computing the ground state energy. So one of the important problems in quantum chemistry or also in physics is to estimate the ground state of a system and, for example, measure the ground state energy. These are two of the most famous problems. People always want to do these kind of computations in quantum chemistry. So quantum algorithm is a hybrid algorithm, and it has some steps which are mentioned here. So we prepare some initial state on a quantum computer. Say it can just be O or a lot of qubits, and everything can be a 0 state. Then we want to obtain some good ansatz by acting with some unitary operator, which depends on these theta, capital theta, which are some variational parameters, which are parameters which we can tune. So for example, then the psi, which is the ground state ansatz, is given by U acting on 0. We started with 0 and we ended up with psi. And then once we have this psi, we compute the expectation value of the Hamiltonian sandwiched between these states, like we are familiar with in quantum mechanics, and see what the energy is. Then we go back to this step, change these theta parameters, and see what the energy is. And we eventually want to converge to the lowest energy, and that is the ground state energy. And we repeat this process going from between 2 to 3, repeat until a convergence is achieved with a desired accuracy. So if you want to have some sort of accuracy, you can repeat this process. Now, the thing to note is that the first step is on a quantum computer. The second is a quantum computer because I'm acting with unitary gates, which are quantum gates on some state. The third is the hybrid part because we measure the energy on a quantum computer, but we optimize the parameters using classical optimizers like gradient-based or non-gradient-based optimizers, which are well known. And then we repeat it until convergence. So this is one of the most famous NISQ era quantum algorithm. So what is NISQ era? NISQ is an acronym for Noisy Intermediate Scalable Quantum. It just tells you that right now we cannot do the problems which we really want to do because we don't have so many qubits and those qubits are not error corrected. So we are in this noisy era, intermediate era, where we can do some computations or we cannot do some other computation. But beyond the NISQ era is the era where we have the quantum supremacy, which people call. And quantum supremacy is the era where quantum computers can solve some problems which classical computers cannot solve in thousands of years. And we have not strictly reached that era, but probably will do in this decade or next 5 to 10 years. Okay, now, one of the things which I did not mention and which is important is I told you about ansatz and I told you about optimizing, but what is the Hamiltonian? What is the Hamiltonian I'm looking at? Hamiltonian can be anything. It can be any 2 to the n by 2 to the n matrix. Now, how do we represent that Hamiltonian and do these measure energy on a quantum computer efficiently? If n is a very big number, it's not optimum, right? And here comes one of the important ideas which people use a lot, which you might be familiar with or might not be, but it's very interesting and you should convince yourself that this is true, is that if I have a Hamiltonian of a given size, two to the n times 2 to the n, where n is, say, the number of qubits, then this Hamiltonian can be represented in terms of Pauli strings. What are Pauli strings? Pauli strings are Kronecker product of Pauli matrices. So if I take a Pauli matrix, I take 3 Pauli matrices, X, Y, Z, and identity, and I have a given Hamiltonian, which is size 2 to the n times 2 to the n, the Pauli matrices and the identity form a complete basis. They form a complete basis in the sense that you can represent any 2 to the n by 2 to the n matrix as Kronecker product of Pauli, like I have mentioned here. It's called Pauli string because you combine a lot of Paulis together. That's all what the string means. The string can be of length n based on the size of the Hamiltonian. So if the Hamiltonian is a 64 by 64 matrix, the Pauli strings will be of length 6, because 2 to the 6 times 2 to the 6 will represent the Hamiltonian. So every term in the Hamiltonian can be, Hamiltonian can be decomposed into large number of terms, all of which depends on 6 Pauli matrices. And how you decompose that is depending on the Hamiltonian which is given to you. Yes. Oh, sorry, yeah. So the question is, if I have some sort of a Pauli string, can I make it shorter, or can I optimize those strings? So the answer to that is, if it is possible using the commutation relations, like you have to represent a 64 by 64 matrix, right? Now, you should at least, like, if you have to represent the non-zero terms in that Hamiltonian by some combination of strings, there will be different terms in the Hamiltonian. They might commute with each other, so you can measure all of them simultaneously. But I don't understand what you mean by like it's not possible to write a 64 by 64 matrix in terms of a 8 by 8 matrix. So you always need these number of Pauli strings. You can insert identity. If you are saying that, okay, I can write in terms of using the commutation relation or thing like that, you can write, and yeah, that's fine. But what I'm saying is, at the end of the day, it's still a 64 by 64 matrix. Yeah, this x, y, z, x, y, x might be equal to y, z times identity matrix of size 16, for example. It's possible, yeah. Those tricks can be done. But once we put it and compute the expectation value, it should, like, it can manipulate those things, and it's sometimes difficult to do by hand. So what we really want is look at whether different terms can be measured simultaneously or whether they commute. Yeah. So the question is this choice of basis convention? It's not the most optimum choice. It's just like people figured out when we're doing this. This is not by any means optimum. When you really go to, like, say, I was just trying to do this yesterday. I was trying to do a 1024 by 1024 matrix. So you need 10 strings, and it just like you have like so many terms. It's like no better. It's very inefficient. It forms a basis, but it's probably not the most efficient basis. So people have done a lot of work in understanding. No one works on these like by decomposing the Hamiltonian like this and then writing down. I'm just telling you because this is what you learn when you do the first step and things like that. Because there can be other bases which might be more optimum. I don't know about those things, but yeah. But what is important is the fact that it's like you can write any Hamiltonian in this term. So that's like, okay, that is the starting point. Now you have written it. Now you try to optimize it, whether you can optimize it. That's like something else. Okay, so any more questions? Okay, if not, I'll carry on. So what is the VQE representation? So I have not mentioned what, I mentioned VQE. VQE is a variational quantum eigensolver. Why is it variational? It's variational because it optimizes the energy based on the gradient descent or other classical optimizer. It's quantum eigensolver because, yeah, it's doing a quantum measurement of energies and computing, giving you the ground state energy. So it's called VQE, and it's very well known actually. So what is the first step? The first step is the qubit Hamiltonian. As I mentioned, what is a qubit Hamiltonian? Qubit Hamiltonian of n qubits is a Hamiltonian Hermitian matrix of size 2n by 2n. So you take the qubit Hamiltonian, then you take some ansatz. You can start with 0, 0, 0, then you can act with some gates, and that gates can be very complicated, that can be less complicated. There are a lot of ansatz which is provided in Qiskit. You can check the various ansatz and other things. In the next slide, couple of slides, I'll be showing you an example of enharmonic oscillator. So I'll show you what kind of ansatz I'm using there. So you choose ansatz, and then you have initial parameters, and then you evaluate the energy. So this is starting state. This is the state preparation by acting by that unitary evolution. Now you have this state, and then you compute the energy expectation value by measuring the independent Pauli strings. So you have Hamiltonian written in terms of K terms. So you measure each of them using these rotation gates and things like that. On a quantum computer, you measure the expectation value as a function of theta. Then you repeat this until you minimize E theta. And then you say, okay, for this value of theta, I obtain the ground state energy. And this is how the step works. This is not a foolproof method in the sense that most of the times it works, sometimes it doesn't work. You really have to fine tune it. But this is one of the best algorithms we have. There is a lot of improvements people have proposed. This algorithm was proposed in 2014, but since then there have been like many research articles written about this algorithm and its improvements, and people are still working. This is one of the flagship algorithms which people use nowadays in quantum computing. Okay, so as I already mentioned, Pauli matrices are special because they form a complete basis set. What happens after that is that, as I mentioned, we can rewrite 2n by 2n matrix using Pauli matrices, or you can also write a 2n by 2n matrix using creation and annihilation operators. For example, these are the operators which we know in harmonic oscillator. So in fact, when we do, so this is all qubit-based approach to quantum computing. So here we want to write it in terms of Pauli matrices because we want to deal with 2 by 2 matrices. When we do Q modes approach, if we reach to that point, there's an alternate approach using Q modes. And in that case, you don't have to rewrite the Hamiltonian in terms of Pauli strings, but you have to rewrite your Hamiltonian in terms of bosonic operators, in terms of the creation and annihilation operators. Because Q mode uses quantum mechanical oscillator, and that approach to quantum computing based on photonic quantum computer makes use of oscillators, doesn't make use of 0 or 1 state, makes use of the infinite tower up to some cutoff of the Fock space, as they say, the eigenstate of the number operator. So you have to rewrite, in that case, we have to rewrite the Hamiltonian in terms of A and A dagger. We'll come back to that later if we get time. So the strings of Pauli, we have already done that. This is one of the important papers which was written. They computed the energy using variational methods for a hydrogen molecule or a beryllium hydroxide, BeH2. This is, you can refer to this paper if you're more interested. For example, what I will talk about is, I want to talk about, say, 8 by 8 enharmonic oscillator. So we won't go to a very fancy system which has a Hamiltonian of a very big size. We'll just focus on 8 by 8 enharmonic oscillator. And suppose I take the harmonic oscillator and I turn in some value of the coupling, cubic or quartic coupling, you get a Hamiltonian. Once you get a Hamiltonian, you check its Hermitian. Okay, it's Hermitian. Once you have the Hermitian matrix, then you can decompose it into polystrics. And that is what I am doing here. You can find more details in the article, but this is what I get. You can see that it's 8 by 8 because there are three. The length of the polystring is 3. So for example, X, ZX, Y, identity Y, Y, X, Y. And these are the number of terms. So you can already see that even for an 8 by 8 Hamiltonian, a lot of terms, they can be simplified, but this is what you get. So you have a code which you feed in the Hamiltonian matrix. It gives you this output in terms of polystring. Okay. It's also built in Qiskit. So once we have this Hamiltonian, we then go and do this setup. So this is the basic setup. I don't, yeah, let's just explain it rather than just going and doing everything, because that will take more time. So we import the usual libraries. You can, you have this code. If you don't have this code, I can put it online somewhere. You can access it. There are other ways to have this code. Just ask me if you cannot copy paste, if you want to play around with this. So we import the basic libraries. We import the poly matrices like X, Y, Z, I. We import the VQE, and then we have to import some optimizers. So we use different optimizers here. This is called SLSQP, which is a gradient based method. It has some full form, I don't remember now. But this is another optimizer which is non-gradient based. So you can optimize based on gradient descent, or you can do optimization which does not use a gradient descent or uses something else. So there are different ways. You use both of them and then see which one is working well and try to see the convergence in the energy. So this is the basic setup. And then I rewrite the same Hamiltonian, which is given here in terms of poly matrices. So HPS is the Hamiltonian matrix, which is given by this in terms of X, Y, Z, and I. Okay. Now, what do? I have the Hamiltonian in terms of poly matrices. What do I want to do? I want to take an ansatz. What is the ansatz? This is ansatz which already comes with the Qiskit, which is ansatz based on the number of qubits. So number of qubits is 3 because the Hamiltonian is 8 by 8 matrix. And there's this ansatz called efficient SU2 ansatz. So it's like a SU2 layer in the sense that, so SU2 is a gauge group or group which is generated by, has 3 generators. So n square minus 1 is 3. So the poly matrices are the generators of this group. So you can construct an ansatz based on how you act with poly matrices. It's called efficient SU2 ansatz. And you can see that this ansatz has entanglement, and for example, you can use RY gates, which is the rotation around Y axis or equivalent to poly Y, related to poly Y, sorry. And then you can also use RX and things like that. So you can play around with different things. And you can see here, I've commented this one of the optimizers and use one of the optimizers because this works better than the other one. And how do you run that? You run the VQE just like using basic command, which comes with Qiskit. You call VQE, give it the ansatz, which is here, variational form, and then give it the optimizer, which is the optimizer here, and then you just run the circuit. And then once I run the circuit, I know the exact value of the enharmonic oscillator because it's like solved since like past 70 years ago or 50 years ago. So we know the exact value of the ground state energy for some given value of coupling, G. So we have this exact value, and then we compute the VQE value. And if you run all this code, fortunately, I cannot right now, but I can show you after the lecture if you're interested. If you run this code, you find an accuracy of 10 to the minus 4, 10 to the minus 5. So it's very efficient in the sense that it really gets that ground state energy to a very good accuracy. So this is one of the applications of VQE to an harmonic oscillator. Now you can be adventurous and you can think, okay, going from an harmonic oscillator, can I do VQE for other models? Say, can I do it for a Bose-Hubbard model, and can I do it for a scalar field theory or other model? And those people write papers about those things and study those models. So there are several models. This is like a basic introduction, but there are more complicated models you can study, obviously. You can, the first thing to do is that you write down the Hamiltonian and then work this out. But one of the things you could have asked me, let me ask, is there any question at this point? Okay, no. So one of the things you could have asked me actually is that why are we doing all this when the Hamiltonian is 8 by 8 matrix? Like, why do we need to write so much code for 8 by 8? Like, I can just diagonalize and look at the minimum eigenvalue, which is what people in exact diagonalization do. And that's a very good question. That's exactly true. If you do exact diagonalization, you will get the same answer. The point here, however, is not that you can do exact diagonalization. The point here is that once you scale the system up, that is, go from n equal to 3 qubits so to n equal to 40, the exact diagonalization will die out. You cannot do exact diagonalization after more than maybe 15, 20. Try doing exact diagonalization for 20 spin Ising chain. You'll run out of steam at some point. But this problem will scale better because there are quantum parts built in it which scale better. So even though for 3 qubits, 5 qubits, 10 qubits, you can still do both of them sufficiently okay, well, but this will scale better. And that is why people are interested in these kind of algorithms, because if you understand them completely and go beyond the NISQ era, then we can scale this much better than you can do any other method. And that is why VQE is promising. But right now, it's like maybe not that advantageous, but in coming years, it will surely be more useful. Okay. Now, after discussing an harmonic oscillator, I want to go back, I want to go a step further and tell you about another model. So this is like, yeah, sure. Oh, yeah, that's right. Now this is what I left here. So I wrote some fixed value. So G is set to something. G. Yeah. Let me remember. I think G is. Yeah, I'll tell you later on. But maybe, yeah, G is something I just completely forgot. I think it's in the article, but I don't have it here. Okay, so the basic idea is this string I generated was with some fixed value of G, and that is why these coefficients are dictated by that. But I somehow forgot to write down the value of G, or maybe copy it when I was copying it to the presentation. I forgot. Okay. Yes, that's good. Now we'll like move ahead in complexity level a little bit. I will try to still be clear. I'll still try to be yeah, I'll try to go slow and be so that you can follow me, but it'll be a little more complicated. So as I mentioned before, this is all good. We have understood what to do with VQE and look at harmonic and harmonic oscillator, but there are other models we want to study. So for example, people want to study scalar field theory in 1+1 dimensions. I wanted to look at this O3 model, which is one of the famous models in physics, at least in 1+1 dimension. What is a O3 model? O3 model is a very simple model. It's like you can think of O3 model as a rotor model. So think about a 3-component vector, right? N1, N2, N3. And think about them at, say, some site 1, site 2, site 3 at each site. At each site, think that there is a 3-component vector, but with some special conditions. What are the special conditions? The special condition is the square of the vector ni dot ni is 1. So it's a unit 3 vector. Now, for this model, what you can do is you can rewrite the Hamiltonian in terms of 2 terms. The first term is known as the kinetic term. The second is the interaction term. Why is the first term known as the kinetic term? Because it just depends on how the rotor model, or what are the possible allowed values of angular momentum at that site I. What is the interaction term? Interaction term is something which couples the nearest neighbor. So I and J are nearest neighbor in this case. So I can take I to be 5 and to be J to be 6, 6, 7, 7, 8, and think and like that. And this is a dot product of those 2 vectors at site I and I+1. And that is what the Hamiltonian is. Now, if you rewrite this Hamiltonian, the I and Ij are the sum over the sides, but what happens is the angular momentum states can take any possible values. So when I do angular momentum in quantum mechanics, the eigenvalue is L plus 1, proportional to L plus 1, right? But L can take any value, integer values, 0 through n. But that's a problem, right? Because if it takes infinite value, then like what is like how do I represent my Hamiltonian? Because Hamiltonian is technically infinite by infinite matrix. So you do some sort of a truncation. You say that, okay, I will take this rotor model or model which represents angular momentum, but I'll truncate the maximum state to be something. I won't look at angular momentum of more than 5 quanta, or maybe I won't look at L plus 1 where L is greater than 5. And it turns out for most of the practical purposes, that is a good enough approximation to get the interesting physics. And that is what we call L max. So L max can be some integer, say 4, 5, or whatever. How does the Hamiltonian size varies with L max and n? It varies like this: L max plus 1 squared, L max plus 1 raised to the power 2n. Now, why is it this weird power? When I told, when we saw that the power for the n spin half particle is 2n by times 2n. So it's very easy to see it. So if L is 0, the possible values of m quantum number is 0. If L is 1, m can take values -1, 0, 1. If L is 2, it will go from -2 to 2. So in this case, it's 1. In this case, it's 3. In this case, it's 5. If you take L max of 0, you see that the local Hilbert space is just one-dimensional. If you take L max of 1, you see that the local Hilbert space is 1 plus 3, which is 4. And if you take L max of 2, the local Hilbert space is 1 plus 3 plus 5, which is 9. And there's a pattern. The pattern is it's always L max plus 1 squared. So the local Hilbert space dimension is not two-dimensional anymore, because this is not like a spin-up, spin-down system. This is like an O3 model, which has continuous, O3 is a continuous symmetry. So it's, technically speaking, the Hilbert space is infinite dimensional, but we truncate it, so we get to some finite number. And that is given by L max plus 1 squared. Now, if we just replace 2 by L max plus 1 squared as the local Hilbert space dimension, you can see that that should be the size of the Hamiltonian matrix. So the n-site Hamiltonian is given by this size. So you can already see that it really grows quickly with L max and also with the number of sites. So it's very hard problem. So you cannot do exact diagonalization beyond some value of small value of n and L max. Okay, one can also study this model using theta term. I don't do it here because that is a little more complicated. But this is the plain Hamiltonian. Now, one of the things is that we have to express this Hamiltonian, which is this in terms of qubits, if we want to understand this model using VQE, right? Because VQE is writing the Hamiltonian in terms of qubits. And those people often do sort of, the standard tricks is to use some sort of transformations, which are Jordan-Wigner and other things, which you can probably know about. So let's look at this model. So this is a four qubit model first. So this is from this paper by some authors in UK. This paper came out last year in December. I'm just showing this paper because it's like easy to understand, and you will understand and can draw the parallels to an harmonic oscillator or the other sort of things we have done before. So this is a 4-qubit state. What are these gates? These are the RY gates. We know what RY gates is. RY gate is just rotation along the y-axis, which is related to the poly Y gate. And then you have some sort of unitary operations, U1 going from U1 through U6. And then you measure the Hamiltonian. So this is like ansatz. So you start with this. This is the unitary operator. This is the ansatz. Then you measure the Hamiltonian. It's exactly the same as we were doing for the anharmonic oscillator. Nothing fancy is going on. But you can build another ansatz. You can build. So ansatz can be anything, right? It depends on the parameters which you optimize. So maybe this is a better ansatz of starting with this, doing some sort of a unitary transformation using 2-qubit gates between neighboring sites, and then doing another set of gates around. So U1 to U3 is two qubit gates, and then you follow it up again with a second layer, which is U4 through U6, and then you measure the Hamiltonian. So this is like the ansatz they used. Okay, now once we have the ansatz, we measure the Hamiltonian. What do we get? Okay, so let's see what do we get. We get something like this. So the results shown here are for different values of coupling. So these are the couplings which was there in the Hamiltonian. And these are the tensor network methods. So I told you at the starting of the talk that classical method is the tensor network method. And now we are doing a variational method. So if we get some answer from variational method for a system which is not exactly solvable, how do we check it? We check it just by doing a tensor network calculation of the same thing and seeing whether the quantum computer gives us the exact same result. So they compared the results obtained using VQE, which is the top two markers, with the tensor network results, which are the lower ones. And it seems like on, say, 5 to up to 10 sites, it seems to agree well with the ground state energy normalized by the number of sites. But as soon as you go to very strong coupling, which is kind of the interesting regime for taking the continuum physics, because this is, as I said before, O3 model is similar to QCD because it's expected to be asymptotically free, in the sense that as you go to higher and higher energies, it becomes free. So in reality, it's like the large beta is the interesting regime. And we see that the VQE does terribly here. The VQE has no convergence to the classical tensor network computations. And I think this is the only result for VQE which is there in the literature. People have not looked at this very carefully. And it just clearly tells you that there's some choice of answers which will probably help us get to the convergence, or maybe it's just too hard. We don't know the reason. So this is something I've been exploring recently, looking at this. But there's another way to think about this. The another way to think about this is, you might say that, okay, if the Hamiltonian is written in terms of these unit vectors, it's this matrix, why do we really need to represent it using qubits? Why can't we use some other basis, say oscillator? Why can't we think about this model in terms of harmonic oscillators? And that is what we are doing right now. And we're trying to understand this model, not from the qubit perspective, but from the perspective of a harmonic oscillator. So the thing to do is that you express the same Hamiltonian, not in terms of Pauli strings or of these size and things like that, but in terms of harmonic oscillators, in terms of A and A dagger, and then see if it gives you a better convergence. So that is the basic idea. Now, if you remember, one of the first things I said about why Feynman was interested in quantum computation and other things is to really look at the time evolution of a quantum system. Time evolution of a quantum system is a notoriously hard problem, and more so with time evolution of a real interacting quantum field theories. So if you remember, the title was, what can quantum computing teach us about quantum fields? The eventual goal, which like most of the physicists want to understand, is, can I understand time evolution in real time? Not using lattice QCD is Minkowski, Euclidean space. You do every rotation. It's like sort of a transformation. The real world universe we live in is real time. So can we do a real time simulation of some interacting field theory? And the answer is, right now, we don't have any good tool. If you tell me that here is my 4-dimensional interacting field theory, and I want to understand how the correlators or how something behaves with time evolution, there's no method which can tell you exactly. There are approximations, there are answers you can get, but it's very hard problem. So the biggest motivation for a physicist is to understand the time evolution of a quantum system. So I have not spoken about that yet, but now we have all the ingredients which we need to understand the time evolution. So let's start to understand that. How do we do that? Let's say we are dealing with 2-qubit systems. So we are dealing with 2-qubit system. The Hamiltonian is a 4x4 matrix. How do we initialize the qubits? We initialize it in this state vector, 0 and 0. Now, I give you a local Hamiltonian or some Hamiltonian of some spin system written in terms of Pauli strings. Let's say the Hamiltonian is given by this, xx plus yy, right? Now, this is XX plus YY because this is a two-site model. So there is X on site 1 multiplied by X on site 2. This is a nearest neighbor Ising model kind of system. And there's Y on site 1, Y on site 2. And that is why this is the Hamiltonian, right? This is a very simple Hamiltonian. Now, I want to do a time evolution of this Hamiltonian. That is, I want to construct a unitary operator that is exponential of minus IHT for some given amount of time t. And I want to ask, what is the state? What is psi t? Now, as I already discussed before, it has to be represented by unitary gates. So how do we do that? One of the things is to represent this, the time evolution of this operator, e to the minus IHT, you can convince yourself, or you can talk to me later, that this is the circuit we need. Now, we know everything which is in this circuit. This is a C0 gate. This is a Hadamard gate. This is C0. This is rotation around the z-axis by some alpha parameter, because you have to specify the amount of angle. So this is like alpha. What is alpha? Alpha depends on the coefficient. Alpha depends on I and t. So it depends on time, for example. Alpha will be directly related to the time. And then you have, again, you have C0, H, and C0. So you can already see there are 1, 2, 3, 4. There are 4 single qubit gates, and there are 4 2-qubit gates. In total, there are 8 gates to simulate the time evolution of this simple Hamiltonian on a two-site model. This already tells us that the problem will get complex very quickly. So, for example, one of the problems with these methods is that you cannot take alpha to be very large. You cannot just say that alpha is a very large number, because then you will get a lot of noise. You have to make small rotations, and the parameters should be small. So what alpha is, you have to split this. If you want to simulate up to time t, you split it into n copies of this circuit. So this circuit is like a small dt. I repeat it, 2 dt, and repeat it n times, n dt. And that is what we get. So the number of gates required for this simple case is 8n times the number of steps I need to take. So 8n. And that's a huge number, because n can be 20, 40, 50, something like that, depending on the accuracy. So this is very complex. But even then, let's just see the basic fundamental. This is XX plus YY. How did I write this circuit down? This is one of the important points. Suppose I had a Hamiltonian like ZZ, just a simple 2-qubit Hamiltonian, which is given by ZZ. And I want to simulate up to time of alpha of 2. So this is e to the I HT. Now, how do we do that? We construct some initial state. We do a C0, RZ, and C0, it will give me psi at t equal to alpha by 2. Now, you can go back and check that the exponential of this indeed gives you is equal to this. So if I plug it into Mathematica or some software, e to the I alpha by 2, Kronecker product of 2 polymatrix Z times Kronecker polymatrix Z, and it's exactly equal to this. And how can we rewrite this? You can rewrite this from the matrix representations, or you can just, like we did it for the cases before. So this is for Z cross Z. And Z is also known as the computational basis. It's the basis because in quantum mechanics, you want to make computation in some basis. So it's like a computational basis. If you have a term like X cross X, how do you do that? You note that the polymatrix X is related to polymatrix Z through this transformation. If you put a Hadamard on the left and the right of a poly Z, you get a poly X. And this is exactly what it is. So you take the circuit for e to the power alpha by 2 Z by Z, which is this. Put a HH on the left, put a HH on the right, it will give you the time evolution of this circuit. And similarly for Y and Y, you have the middle part is the part which is shown here, and then you stick in HY on the left, HY on the right, where HY is this matrix, where This is the relation between poly Y and poly Z. So this is how you can very naively do time evolution of quantum circuit. But this is very complicated. No one does it using this. This is good to understand what is going on and how to implement it, but this is highly non-efficient. There are other efficient ways of doing this, but I won't have time to go into that. But we can chat more if you're interested. So this is how we can simulate Hamiltonians of which have terms like xx plus yy or some other terms. Okay, so there's another demonstration. Yes, that's good. So you can play around with this. I'll just briefly explain what this is doing. So this is a quantum circuit of 2, 2 classical bit, 2 quantum bits. I'm specifying the time, which is 0.1. And then I'm applying the Hadamard to the 0th qubit 0, Hadamard to qubit 1, and then doing Cx to 0 and 1, some set of gates, which is exactly what was shown here. If I want to implement this, how do I do that? That is what the circuit is doing. So Cx, H, Cx. And that is what this does. H on 0 and 1, Cx on 0 and 1, and then Rz. And the parameter of Rz is T, right? Because as I mentioned, this alpha depends on the time. That is why you see that this Rz has a coefficient time, T equal 1. And this is what we have. Now, one of the important things to see is if you do this and measure the circuit, you will find that the input state, which was 0, 0, is not the same as the output state. Output state is something else. You start with 0, 0 state, but you time evolve into something else, which is not the 0, 0 state. One thing you can check is just put T equal to 0 here. What should happen if I put T equal to 0 here? What should be the output state? Huh? Exactly. And you will see that from the code. Because there is no evolution. T equal to 0 means I'm not doing any evolution. Input is the output. Like it's like e to the 0 is identity. So I'm multiplying the input state by identity. So if I just take this circuit and want to convince ourselves that whether this circuit is actually doing the right thing, one quick hack is to just put T equal to 0 and see whether you get the same input. You create some random input. Doesn't matter you create in 0, 0. Create some random 2-qubit state with some weird coefficients. And set T equal to 0, you'll get back the same coefficient. So that just tells you that this circuit indeed represents time evolution of that input state for whatever time you want to put in. Remember that you cannot put in a very large number here. As we already discussed, it will give you some state which is probably has some noise and other things. You want to keep these parameters small because you want to do small rotations on the Bloch sphere and things like that. So this is a simple demonstration of how this circuit can be implemented. And you can measure the output state, and then you take 1024 shots. Usually you can take 2000, 8000, whatever number of shots. It will give you the state. So for example, if it is say 0, 0 plus 1, 1 divided by square root of 2, then you will see that around 510 times or 512 times you get one state, and other 512 you get other states, but it's not exact. There's some noise. So maybe you'll get 500 and 524. So that means that it's a uniform superposition. So this is just a way of, and then you can make a histogram of those counts. So you can do that. Okay, how much time do you have? Maybe, okay, yeah, I think I can go ahead. So now, after discussing all this, you might be interested, some of you might be interested in knowing the experimental point of view, like from people who actually developing these hardware. We as a theorists are not very interested. We want to run something on a quantum computer. But there are people working all over the world on these photonic experiments using quantum optics, manipulating the lasers and trying to see how we can make it a viable hardware for quantum computations. So for that, we need to use an alternative approach, which is not just based on two-state or a two-state system or a qubit methods, but which is a quantum mechanical harmonic oscillator, sometimes also known as continuous variables. So for example, let me just quickly mention the difference between the continuous variable and qubits. We have seen all of right side. So Once you know all of right side, you should be able to understand, like you can make opinion of what it is. So qubits is Q modes, goes to Q modes. The poly operators X, Y, Z now becomes the mode operator or the number operators of the harmonic oscillator, A and A dagger, or the quadrature operators X and P. So quadrature operators are operators for the position vector and the momentum vector, which can be written in terms of A and A dagger. So those are known as quadrature operators. Now, poly eigenstates, for example, the ones I was showing on the Bloch sphere, 0, 1, plus, minus, and things like that, they now become some states which are eigenstates and states corresponding to the harmonic oscillator. Say, for example, coherent states, squeeze states, and number states. Then the corresponding gates, which we discussed, like the phase shift gate, Hadamard gate, C0 gate, now become gates which are unitary still, but now depends on these mode operators. Those gates are known as rotation, displacement, squeezing, beam splitter. Now, from beam splitter and squeezing, you already make out the connection to experimental people. So when you take when experimental in lab, you take two lasers, you want to like split the beam or pass it through some sort of a mirror or something, and those sort of gates are implemented in this strawberry field simulator, and they are known as beam splitter gate. So you can split the beam at 45 degrees, 60 degrees, or whatever. And the squeezing is the squeezing gates corresponding to the squeezing of the light. So there are interesting things you can read online. I won't have time to go into the details, but try just to search squeezing of light. And then you will see a lot of articles how people squeeze light or squeeze photon, for example, in the lab, and how they are important and are related to the unitary transformations in this approach to quantum computation. So this is using Q modes or continuous variables. This is using qubit. So one of the advantages of not using a qubit method, but using a continuous variable method is that think about bosonic systems. What is the difference, fundamental difference between bosons and fermions? The fundamental difference is the Pauli's exclusion principle. It says that no two fermions can occupy the same state, the same set of quantum numbers and things like that. Right? Fermions, say, for example, spin half can be up or down. There are two states. But what about a boson? Bosons don't necessarily have a two-state system. They're infinite dimensional. You can have a boson, it can be hopping around anything. All of them can condense to one site, like Bose-Einstein condensation, or all of them can be, they can do weird things. So for example, when we are dealing with systems which have bosons, like say Bose-Hubbard model, or say systems with continuous symmetry, O3 model, or say some other model, it might be more natural to think of them in terms of continuous variables, because maybe two-state system is good enough, but maybe continuous variables is a better way to think because it's more natural, because it's of the infinite dimensional Hilbert spaces. So that's why people started looking at Bose-Hubbard models with continuous variables. And for this, the Hamiltonian is written in terms of not Pauli strings, as you can see, but in terms of creation and annihilation operators, AI dagger AJ, and N is the number operator, which is defined as A dagger A. And you can rewrite the Hamiltonian, and then we know the matrix representation of creation and annihilation operator. So we can write the Hamiltonian, and then you can basically rewrite the Hamiltonian and then do a Hamiltonian simulation of that Hamiltonian using something called a Lie product formula. So if you have a Hamiltonian which is composed of two terms, A plus B, you can decompose it like this using the well-known Lie product formula, and then you can rewrite it like this in terms of gates such as beam splitter or rotation gates, similar to this, right? Because if we want to do a continuous variable approach, we want to rewrite the Hamiltonian in terms of A and A dagger, but rewrite the unitary evolution in terms of these gates. So that is what this process does. And similar to what we were doing for qubit language, you can represent the time evolution up to you can put a negative sign here, it doesn't matter. In terms of these gates, and you have to do this n number of steps, and these are the parameters for those gates, and people obtain interesting results. And for example, this is how a single time step circuit looks like. This is a beam splitter gate. This is some higher polynomial gate known as the Kerr gate. This is the rotation gate. And if you're interested, actually, there's very nice articles on this Xanadu's web page And this simulator, which people use for these kind of things, is called Strawberry Fields Photonic Simulator. So you can play around with that. It's very similar to Qiskit, just that Qiskit is everything is two-state polymatrices, but here everything is in terms of oscillators and A and A dagger, X or P. So it's nice to play around. Sample code is given here. So in this case, I'm playing around with, say, Bose-Hubbard model with different values of coupling and coefficients, and then I prepare a state. So in this case, remember, now we have to not prepare states like 0, 0, we have to prepare Fock state. Fock state, Fock 2 means it's a number state with 2 photons. If it is 3 photons, then it's 3, Fock 3, Fock 4, and things like that. So you have to denote the states. So the first Q mode has 2 photons in it. If I don't specify anything, it has 0 photons in it. So you consider those states and do the time evolution. And again, in this case, you can check that if I put t equal to 0, as I have done here because I was checking the code, that it will give you the input state. If you put in some other value of t, you will see that it goes to some different value of psi t. So that is what you can play around with. One of the things which people compute is the probabilities of the state, Fock state, probability of overlap. Say, suppose you start with 2 photons in some state. What is the probability that you end up with 0 photons? Or you start with 1 photon, 1 boson. What is the probability that you stay in 1? And so on. So you can compute these probabilities. They all add up to 1. But these are probabilities at a given time, psi t. They depend on psi t, whereas the input state was psi 0. And then you can sum the result and see it's equal to 1 and things like that. So I suggest that you play around with this. I don't have time to, unfortunately, do and show you this. But you can install Strawberry Fields on Google Colab or your own laptop, and you can run this code and see what happens. Okay, so with that, I think I've covered most of what I wanted to do. Let me just briefly summarize. I like to think about this as we are entering a new era. It's similar to what lattice gauge theory is, about which I'm sure you have heard in the summer school and know. Did it with classical computers in the 70s. So people suddenly started wanting to look at physical theories on classical computers, lattice gauge theories. Now we're basically reaching a point where we want to understand the physical theories on a quantum computer. And the basic idea is to solve some toy problems with current hardware and current quantum hardware we have access to. But this is not going to be anytime soon, probably for problems which we really are interested in. It will take like decades or more than a decade. And the part of the reason is quantum mechanics is quite restrictive, unlike classical computing. So the progress might not be smooth. In fact, it will not be smooth in most likelihood. As compared to classical computing, because even the error corrections and things like that is more subtle for quantum mechanics than it is for classical computer. You don't worry about the result on a classical computer because the possibility of error is minuscule, but that is not always true for quantum mechanics. So error correction is a major part. You probably never heard about the error correction in your computer because no one cares about it, because 550 billion transistors, probably one of them goes bad, doesn't affect your result or something like that. But for quantum mechanics, it's different because of the properties of entanglement, decoherence, and superposition. But for now, VQE plus variance is the state of the art. A lot of new methods will come and it'll help us understand more interesting physical systems in the future. So I hope you get interested, and thank you.
All right. So I'm curious if there's any like quantum computing analog to a problem that can't be solved in polynomial time, but like a solution can be checked in polynomial time, if there's like a quantum equivalent for that.
Yeah, it's called QMA.
Right. So do we know of any problems that could be checked by a quantum computer in polynomial time?
Oh, you're asking about what problems are there in QMA? Yeah. So for example, computing the ground state of a Fermi-Hubbard model at half filling is an example of QMA complete problem. That means if you give me the ground state, I can tell you whether it's the exact ground state.
Okay.
Because I have to compute the energy for that ground state, right? But I cannot keep constructing the ground state is not possible. checking the solution. So most of these problems, it's either BQP, which is in solving polynomial time on a quantum computer, or it's QMA. QMA stands for quantum Mellin Arthur. It's like analogous of NP hard in quantum language. Yeah. So you can check a lot of things you can find online. Just check for spin glasses, QMA complete, and things like that. You'll find a lot of interesting stuff.
Okay, thank you.
Yeah.
Well, I'm sure we're gonna talk a lot later, but just so that you can talk about, IBM said that by 2033 they want to have 100,000 qubits. That's probably
I don't know anything
dream.
about that.
Yeah, but if when we manage to get to some thousands of qubits, what possibilities do you think will open up?
So one of the things which we always want to keep in mind is that someone's 200 qubits might be as good as someone else's 100 qubits. And there's a reason for that. The reason is what people call just having a qubit and having a logical qubit is different. Having a qubit is like you have prepared a two-state system. Okay, fine, that's qubit. But logical qubit is that something which can be used and manipulated and can keep its coherence over a long period of time, with which you can do meaningful computation. For example, where the error rate is not as much. So for example, 200 qubits with an error rate of 20% might not be even as good as 100 qubits with the error rate of 1%, something like that. So first of all, whenever someone's saying number, we have to understand error rates and things like quantum volume, because that is related in some way. But yeah, I think for most of the practical purposes, for physics point of view, lower dimension, you definitely need order of million logical or 100,000 more. Yeah, million definitely qubits. So I would say if the number is close to that at some fraction, it just tells us how close we can get to solving those problems.
Like simulating real systems.
Yeah, real systems, like simulating simple lower dimensional systems might also need like million qubits, logical qubits. There are a lot of estimates you can find online. So people say, okay, this is the error, this is what is the gate frequency, this is what the number of counts is. Depends on a lot of things actually. So based on that, yeah, I would say. But it seems like in the next 10 years, probably advancement of VQ and things like that, we can probably start to understand simple models like O3 or scalar field theory, things like that, I think in a better way. But going to like 4-dimensional QCD, like it's,
no.
I don't know. Yeah, it might, yeah. I don't know when it's for.
We're lucky if we do see it someday.
Yeah, I agree. Yeah. Good. Any more questions?
Okay, then we can close it here. And the next thing will be 4:30, the Hack Social. Everybody's invited, students, friends, speakers, and so on and so forth. But thanks, Raghav, again.